Hello and welcome back to Leonard's Education Centre. Today we have 3.4 materials from OCR A level Physics, which I conveniently forgot to include. I am Lena, I am your host today, and as always please note that I am only a student. I am trying to help other students out here. If I didn't feel confident in my own abilities, I would not make a video. Although, with that in mind, if you are still unsure about anything, please check other notes. As you can see looming off to the right here, we have 3.1.4, so let's jump right in. 3.1.4 is all about deformation. Also, one quick thing to mention about 3.4 and physics in general, there are smaller subchapters like this, 0.1 for deformation. It is really hard to find broken up notes into these smaller chapters, so just keep it in mind that you may only be able to find a 3.4 overview. It will be the same stuff, it'll just be everything you see all together. So first off, the thing we need to know are tensile forces. We have a diagram down here as well to look at. These are forces which cause an object to increase in size. So imagine this spring. Imagine this was its original length between these, and the tensile forces will cause it to expand outwards. On the flip side of that, we have compressive forces, which are the exact opposite. They compress the object and decrease it in size. So when an object is deformed either by tensile or compressive forces, and it returns, this is the key part, it returns to its original length, it has undergone elastic deformation. This is a key definition here for elastic deformation. Similarly, if an object has been deformed and this time doesn't return to its original shape or length, whichever you want to call it, these are, in this case, interchangeable, it has undergone plastic deformation. Now, keeping both of those in mind, we have something called Hooke's law. This is by a scientist called Hooke, hence why his law, and it states that the extension of an object is proportional to the force that causes it, provided the elastic limit is not exceeded. We will come back to elastic limit in a moment, bear with me. So the formula for this is force equals force constant, or spring constant if you're working with springs, times extension. This can be rearranged if you need to solve for extension. It'd be F over K equals X. For elastic deformation, as you'll see in a second, work done is the area under the graph, or is represented as this formula here. And we can sub in the formula that we have for F up here. This formula can come down into this F. The end of the arrow is a bit shocking, to give us a half kx squared. X is still extension, k is still spring constant, or in this case, this is force. Both of these can be used, they both work, it just depends on the scenario. So we can see on this graph we have force versus extension. This area here, under the graph in the area of Hooke's law, because as you can see, in this area here, the line is perfectly straight, therefore they're proportional. That is until you reach the elastic limit, which is where you move from elastic deformation to plastic deformation. Then the work done is no longer applicable to this formula here, as we're no longer following Hooke's law. Another point you need to know on these graphs is called ultimate tensile strength, or sometimes it's just ultimate strength. It depends. You can see both. This is the maximum point that force reaches before you start seeing the drop in force for continued extension. And then finally you have either the fracture point or rupture point. Once again, it's got two names. And this is where the object will actually break. For plastic deformation, we see none of this. We see a loading curve and an unloading curve. You can get straight unloading curves that would look something like this. Not as common. You can get them. Now, moving on to 3.4.2, which is Young's modulus, or Young modulus. It is created by a scientist called Young, so you'll see it in some scenario with the apostrophe to show that it's made by him. Most of the time you won't. Just bear that in mind, it's the same thing. You don't need to worry, be confused. So first thing for it we need to know is stress. Stress is the force per cross-sectional area. This is key, by the way, the cross-sectional part. So let's say you had a wire like this. You would need to take the cross-sectional area, so if you had a diameter, you'd need a length as well. So you would work out the area as if it were a circle, so you'd do pi r squared, and you would have to just leave it like that. You don't need to transfer the length or anything. So don't be confused if you see a question based on like a wire cylinder or something like that and you don't get given a length. You don't need one. It's represented as the Greek character sigma. Yes, sigma. And it is force over area, as we've already said, which can be represented as F over A. Its units are pascals. This is a capital P, A, and a lowercase a. Its SI units, however, are Newton meters to the power of -2, or newtons per meter squared. Yeah. Then something else we need to know is strain, which is extension per unit of length. It's represented as another Greek character, this time epsilon. It is a backwards 3, essentially. Quite a hard character when you first go to draw it, actually. To work it out, it is extension over length, which in some cases you'll see as x over L, and in other cases you will see as theta L over L. Oh, not theta, that's delta, sorry. As you've probably seen many times, triangle, whatever, just essentially means change, yeah. It doesn't have units, as it's a ratio, so keep that in mind. There's no units to it, don't put any units. Then finally we can get onto Young's modulus, which is a representation of how stiff an object is. It is represented as a capital E, and it is equal to stress over strain, or sigma over epsilon. As strain, we just said, has no units, and stress has the units of pascals, Young's modulus will just inherit the units it's given. Once again, I believe it has SI units of nm to the -2, but you'll have to fact check me on that one, because I'm not 100% sure. And then the final thing we need to know is 3.4.3, which is how to describe materials. So there's a lot of keywords here. You do just have to know them all. That is a horrible bit of handwriting there. But for ductile materials, they have a large plastic deformation. And they have lots of necking. This is the best representation of necking. So essentially it starts out as a material and the middle bends in until it snaps, essentially. This is most metals. And when we are describing objects, we use E graphs or Young modulus graphs. You may see them referred to differently depending on what scenario you're in. E is just, obviously, as we said down here, the representation for Young's modulus. And a ductile material will have a graph that looks like this. So we will have a small amount of elastic deformation, which is proportionality. And then we have a big area of plastic deformation before it eventually breaks. As for a brittle material, it is almost the opposite. It has very little plastic deformation. However, a key thing here, people always get this confused. It does not mean the object's weak. A brittle material can still be stronger than a ductile material. It just reacts differently when force is applied to it, essentially. So as we can see by the graph, we've got a larger area of proportionality and a very small area of plastic before it breaks. Other descriptions, I don't have a graph for. A key part here, though, is in the textbook and in most examples you can find online, we aren't actually given any graphs for these descriptions. We are just given the word-based descriptions. I'm not sure, however, if this means we can get asked to draw these graphs or interpret these graphs of any of these materials in exams. I don't know. But the other terms we need to know are malleable, which has a large plastic deformation under compression. This is key, only compression. Tough means an object is resistant to its impact forces. Hard means it can resist plastic deformation, but a key part is it's in the terms of like cuts and scrapes, because technically if you were to cut something in half, that would be considered plastic deformation. And then finally we have stiff, which means an object has a high Young modulus, which is small deformation for a large amount of force. And then some other terms, these are still describing materials, but they're slightly differently related. That's why they're in a different color, different section. So we have alloys, which are a mixture of more than one element, one of which is a metal. That is a key part, which I forgot to include. Let's append that. One metal. A good example of this is steel, which is made from carbon and iron. Then we have similarly related composites, which are made from two or more materials that have different properties. And this produces a material with like not necessarily combined properties. It can have biased, it can have totally unrelated characteristics, like it just produces a totally different set of characteristics. An example of this you can see wedged in the middle for some reason is carbon fiber, which is carbon composites, I messed up there, and resin. That's going to be an E now. I'll just give up on that. Let's try again. That is carbon composites. There we go. And resin. Those two together make carbon fiber, which has a mix of properties from carbon strength and resin hardness. And then we have something called polymeric materials, which essentially mean they go from hard to stretch, easy to stretch, back to hard to stretch. You can see that here. So the curve starts quite steep, then it flattens out in this middle section. In this middle section, I suppose to say. And then near the end, it gets really hard to stretch them again before the object breaks. An example of this would be rubber. And then one more key thing we need to know, which again is a little unrelated. It does kind of link in over with plastic deformation down here that we did right at the start. But it's something called hysteresis or hysteresis, depending on how you want to say it. There's different pronunciations. So some materials will absorb more energy than they release. This is shown in the yellow area, and this is hysteresis. So this essentially is the energy lost in stretching. And typically this is most commonly lost in internal heating. Once again, an example of this would be rubber. If you don't allow it to snap on this graph, it would come back something like that, and this area in the middle would be hysteresis. That is essentially everything you need to know in 3.4. That is materials. If you have any questions, feel free to let me know, and I do recommend you have a look over some more concise notes, and this is just a general overview. There is some more intricacies and details that I haven't included, specifically in parts like polymeric materials and alloys and composites. According to my teachers, we shan't need to know much about these, but nevertheless they can still be asked in exams in details, so keep that in mind. Thank you.